Okay. So welcome everyone to the July TEPS seminar. This would be our last TEPS seminar actually for this cycle, and we'll start the new cycle in September. But thanks for making the time to come. I know a lot of you must be on vacation, but we'll get started. We have two TEPS trainees presenting today. We have Simone Delisle and Lisa Dang. So Simone, to introduce you, I'll pass it off to Bjorn. Bjorn, you can introduce Simone.
Yes, so Simon is a PhD student here at the University of Montreal. He started now his third year. We are very excited to kind of diving into James Webb data, and that's actually related to the project that Simon will talk to us about today. It's actually a very intriguing way of using the transmission data to learn something about how the variations across the Terminator are. So we do something like Terminator mapping, if you want. With that, I let Simon present his work.
Yeah, okay. Hi, everyone. So let me just share my screen. So my name is Simon. I'm under the supervision of Bjorn and at the University of Montreal. And basically my talk will be on, what I'm working on and I've been working on for, I guess, 2 years, is mapping the Terminator of exoplanets during transit spectroscopy. So basically, so instead of doing it the usual way where you have a windy atmosphere, doing it with a 3D atmosphere. So before I dive into that, I'll just do a quick recap about the transmission spectroscopy, just to be sure that everyone is on the same page. So usually the way we do transmission spectroscopy is you have a planet that transits in front of its star. And then when it does, you get less flux. So if you look at the light curve, so basically the amount of light that you get, you have a decrease during the transit, and then it goes back up when the planet exits. And this is actually from James Webb data yesterday, WASP 96b. So I just put it in because that was nice. So you do that, and then you compute the flux difference when it's in transit versus out of transit. And you do that for many wavelengths. Then you can plot basically for each wavelength that difference in flux. And what that spectrum tells you, it tells you which molecules are in the atmosphere, because different molecules absorb more or less at different wavelengths. And so let's say here at 1.4 micron, if I have a bump here, so a bump in absorption, it's probably because I have water, because water absorbs in this band. And so having these bumps here tells us that, okay, there's probably waters in this planet, which is why it's quoted here. And this is also from WASP 96b from the data from yesterday. So this is how we do transit spectroscopy. Now, how do we get this nice blue curve here? So like, how do we get this model? Usually what we do is we assume a 1D atmosphere. So what that means is we build an atmosphere that only has variation in altitude. So there's no latitude and longitude variation, meaning that your North Pole has the same temperature and the same composition as your equator, for example. And I mean, this is what we've been using most of the time since the beginning of this field, mostly because the data quality that we add from HST, Spitzer, Kepler, and all that stuff, I don't think the precision was there enough so that we could actually see the systematic error that these approximation yielded. But now with James Webb, we will see the systematic error when we use 1D transit models if you try to fit extreme planets such as hot Jupiters So here I have a GCM. So a GCM, it's basically a physics simulation of a planet, which is really complete, and it gives you basically the temperature and the composition of that planet for every point on its atmosphere. And this is for WASP 121b, done by Vivian Parmentier. And what we can see here is that, so this is the phase. So at alpha equals 0, this is basically the day side. And we can see that basically the day side is really, really hot. The night side is really, really cold. And you can see that there's a sharp transition between these two. And so this planet and pretty much all Jupiters, they really are not fit to model with a 1D transit model. And so the idea was to develop a 3D framework and try to analyze planets such as WASP 121b or other Jupiters to see what we could constrain on this planet. So yeah, so the idea was to develop a 3D framework. I won't go into all the math and stuff because it's going to get boring at some point, but the idea is just you discretize your atmosphere in a longitude, latitude, and pressure grid. And then at each point in this grid, if you want to do the radiative transfer, so like compute the amount of light that is blocked by your atmosphere, you need two things. You need the altitude of each point, and you need the extinction coefficient of each point. The extinction coefficient being basically how absorbing the atmosphere is at that location. Then how do you compute the total amount of light that is blocked? You basically do ray tracing. So you send light rays through the atmosphere, and you basically compute the optical depth and the transmittance of each ray. And then you just basically integrate all these rays to get the total amount of light that is blocked. What is different from 1D model, though, is that the phase of the planet matters, because if you're at the mid transit time, or you're like near the egress or near the ingress, the planet has rotated a bit. And so actually the light absorbed by that planet will change also, because you see a different side of it. This is not the case when you do a 1D planet, because since it's uniform in longitude and latitude, the flux absorbed is the same throughout the transit, but this is not the case for 3D model. So you also need to account for that. And so I'll just show you a couple of plots that some interesting result that we have. So this is a transit spectrum from the GCM that we saw earlier, from a WASP 121b. And I have it plotted for different phase angle, just to not have some confusion. This is not the same phase angle as before. I guess the 0 degree here is just the mid transit point, and then the 10 degrees is 10 degrees. So 10 degrees after the mid transit point, and minus 10 degrees is minus 10 degrees before the mid transit point. And so what we see some interesting effect. We actually see that, for example, in this band here, the green curve is above the two other curves. So bigger phase angle leads to bigger absorption. But here in the water band, so at 1.4, it's actually kind of inverted. And we can try to understand that, why this is the case. To have an idea, we can go back to the GCM that we had. Actually, we see here something that is interesting, is that if we look at the day side again, we see that it's really, really hot, but we also see that there's a asymmetry. The east side, so basically the right side from this perspective, is a bit more hot. The reason being because there's some heat transport to the night side. The heat needs to be transported by winds. So in this case, the winds flow towards the east. So there's going to be more heat toward the east side. So there's actually an asymmetry from east and west. So what is interesting, if we look outside of the water band, so at 1.1 to 1.2 micron, the reason why you get a higher transit depth, the more your angle is positive. So basically we are in the case on the right that I showed here. So this is the star, this is the telescope. And when we have a positive angle here, just means that the Terminator, so the transition between day and night is slanted like that. The telescope we probe this slice here. And so what we see is we actually see when we have a high positive phase angle from mid-transit time, we see that we probe a lot of the day side on the east and a lot of the night side on the west. And this is important because we know that the east side is really, really hot compared to the west side. And we also know that usually if you have a cold part of an atmosphere and a hot part of an atmosphere, they don't cancel out in the sense that the other part of the atmosphere will have much more impact on the transit spectrum than the cold part, mostly because the atmospheric extent of the atmosphere is really, really like it's exponential, basically. So the higher your temperature is, really the higher your atmospheric extent. And so in this case, when we have a high phase angle, we see more of the day side. And since the day side on the east is really, really hot, it just shifts all of the spectrum up because other atmosphere and an atmosphere that is more extent absorbs a lot more. So you get a shift towards more absorption as you see more and more of the east outside. But if you go to the water band, then sure, as you progress during transit, you see more and more of the east side that is hot. But the thing is, water, if you go back to the GCM, is actually, so water would be here. Water is actually dissociated on the day side, so because it's too hot. And so there's actually also an asymmetry in water from east to west, but it's actually inverted. There's less water on the east side. And so when there's less water on the east side, you also get less absorption. So this effect goes in opposition with the temperature effect, which is why they actually kind of cancel out and then another curves win. And so these are interesting effects, but you can also look at other effects from the light curve perspective. Instead of looking at the transit depth, we can just look for a single wavelength or for a single wavelength band. We can look at how does the light curve looks like. Now, if we were to look at the light curve in its entirety, we wouldn't see anything because the effect of a 3D atmosphere is really, really hard to see. So instead, what we do is we just subtract our light curve with the best fitting light curve from a rocky model. And so that way, what we're left with is basically excess absorption that comes from the fact that we have a 3D atmosphere. And these plots are really informative because what we've learned is that basically when you have these really, really big peaks during egress, so this is egress, and I just realized that the axis is wrong. This is not 1000 degrees, but this is basically the egress. And what we realized is that the difference in peak from egress and ingress, so we see here that the peak during ingress is really, really more big than the peak during ingress, actually is an indication of a east and west asymmetry in temperature. And so basically this really big peak here during ingress tells us that the east side is more hot than the west side. And this is something that we can see by eye easily and without doing any retrieval, just by looking at it. And some another effect that we realized is that this slope here, so during the transit, is actually an indication of the temperature gradient across the day and night side, meaning that when we have a big gradient during the transit, it actually means that the gradient from day to night side on the east is actually bigger than the gradient from day to night side on the west, meaning that there's a more rapid temperature change on the east than on the west. And this is also something that we can see graphically, which is quite nice. And so we're still working out the detail on how to use that to retrieve important parameters, but we did some tests with a certain parameterization. So basically, we tried to retrieve the temperature field on the GCM that I showed earlier. So basically, the closest that we can get to real data before we have real data from James Webb. And the parameterization is not perfect, but one thing that we did saw is that it accurately assessed that there's a east-west temperature difference between the east and west limb. So this is quite exciting, and we're still working on that to make it even better framework. But yeah, this is pretty nice for now. So yeah, that's pretty much it, I think.
Perfect. Thanks, Simon. Do we have any questions?
I have a question. This is really cool, and it's really nice to be able to see this like Terminator asymmetry without using a lot of time, without getting a full phase curve. And so this might be like a very like time optimal way to figure out wind direction on these exoplanets. So what are the best target, or what target are most likely to give these like large differences between egress and ingress? If you've looked into it.
I mean, obviously, probably the closer in that it is, the more it's probably going to be super odd, and the more odder it is, then probably the more it's going to be easy to constrain it. So basically, all the WASP target are probably really good, but I know that we want to test it on WASP-39b data from James Webb, which we should get pretty soon. So yeah, I'm gonna try it first on that and see then where it leads to.
Sweet. I hope we'll see something.
Yeah, it would be nice.
Yeah, I guess the technique also relies on that the fact that the planet is rotating. So if doing transit, so the closer you are in, the more rotation happens. And so the more different you see the planet doing ingress than doing egress. So we'll see. So the hottest Jupiters, ultra-hot Jupiters, are probably the best for this.
All right. So ultra-hot Jupiters and fastest rotating. So ultra short period.
Exactly.
Yep.
Any other questions? Okay, if not, then thank you so much, Simone, for the presentation. Now I'll pass it off to Lisa, who's going to present, and she's also going to do her own production as well.
Sorry. All right. Can we see my slides all right?
Yes, we can.
Good. All right. So yeah, hi everyone. My name is recently Dr. Lisa Dang. I defended a couple of weeks ago at McGill University, and I am also an incoming Banting postdoctoral scholar at University of Montreal. And so I'll be joining Simon and Björn and all of the folks from the other side of the mountain in the fall. So I'm here today to give you a quick summary of my PhD work on characterizing exoplanets and their atmosphere with the Spitzer Space Telescope, which is a nice predecessor of all of the images that we received yesterday. So my presentation today will follow the orbital evolution of a gas giant undergoing eccentricity tidal migration. And so first we are going to start beyond the snowline with the Spitzer microlensing campaign. And then we are going to lose a little bit of angular momentum and be sent on an eccentric orbit where we are going to characterize the thermal phase curve of an eccentric hot Jupiter caught in the act of migrating. And then after that, we'll tidally circularize our orbit and go through some of the things that we've learned from phase curves of more typical hot Jupiters on circular orbits. And finally, we are going to have our atmosphere stripped away and look at ultra-short period rocky cores. Along the way, I'm also going to discuss some ideas that have emerged from these projects, which I propose to investigate in the future. So my talk today will mainly focus on, again, like Simon, atmospheric characterization of transiting hot Jupiters. So I'll quickly remind you of the basics. These are gas giants that are blasted with stellar irradiation because they're really close to their host star. And because of strong gravitational interaction and tidal interaction, they're also likely synchronously rotating, resulting in a permanent day side and a permanent date side as illustrated here on this slide. And we're also expecting drastic temperature gradients between the substellar point and the interstellar point. And so as the planet transits, the host star, a distant observer will see a transit as the planet passes in front and an eclipse as it goes behind. But as we observe it over time, we're also going to see different regions of the planet causing variation of brightness over time. So on the right here, I have an example of an infrared phase curve of HD 189733b, where you can see the planet's transit in the middle, the two secondary eclipses at the two ends. But if you zoom in what's in the middle, you also see this modulation here that is caused by the planetary flux. So we can actually take this phase curve and transform it into a longitudinal brightness profile for these planets. And so what I'm trying to get at here is that phase curve are extremely rich in information, even though there are time consuming to get, but you actually see the planet's atmosphere as a whole, as opposed to only the Terminator or the day side of the planet. So if you notice here, the peak of the phase curve is also not coincidental with the time of secondary eclipse, and this is usually indicative of a shift of the hottest region from the substellar point. So to detect these phase variation, we first have to go from images to a raw light curve like the one that you see on top to a reduced phase curve with detector systematics decorrelated from the astrophysical signal like in the bottom. And so over the years, there have been many decorrelation methods that have been proposed to achieve this level of precision. Many of them are listed here. And this motivated us to use an automated open source, to build rather, an automated pipeline called SPCA for Spitzer phase curve analysis pipeline with various detector model implemented to make future phase curve analysis easier and also reproducible. So working on reducing Spitzer IRAC light curves has made me very well acquainted with many of these techniques to remove detector systematics, and that has led me into a short foray into planetary gravitational microlensing. So back in 2014, the Spitzer Space Telescope was given a new role as a microlens parallax satellite, aiming to obtain simultaneous space-based light curve of microlensing events to constrain their mass and the distance to the lens. So even though here the science and the observing strategy are quite different, similar instrumental systematics also plague microlensing light curve. And so we wanted to see whether any of the decorrelation techniques that had been developed by the exoplanet transit communities could be of service for microlensing surveys. And since detector systematics here can sometimes mimic planetary signal that we're trying to detect, and so what I'm showing here on the left is a microlensing event observed from the ground and from Spitzer. The blue dots are from Spitzer and the orange dots are from ground. But if you look in the residual, you also see this like correlated noise in the Spitzer data. And unfortunately, this is also consistent with a planetary anomaly. So on the right, we use a completely different detector model or reduction model where we use pixel level decorrelation. And here, once we use pixel level decorrelation, we see that the structure that you saw on the left did not survive this other technique. And so we think here that we're ruling out this tentative planet detection. So this is it for the microlensing part, but I'll go back to studying climates and atmosphere of exoplanets. So now that we know how to clean these data, what can we learn from them? So repeated observations of EXO-3b eclipses were extensively studied for understanding Spitzer systematics. But the reason I'm interested in EXO-3b is because it's a hot Jupiter with a moderate eccentricity of 0.3, and that's perfect for testing some climate models. So here I'm showing the 3.6 and 4.5 micron Spitzer phase curve of EXO-3b, which I'll show again in the next slide. So as opposed to circular orbits, here the planet's distance to the host star varies across the orbit, and therefore the eccentricity of the planet or eccentric planets give us insights into how the atmosphere responds chemically and thermally to this change of incident flux. And so here are predictions for EXO-3b's atmospheric pressure as a function of temperature, where it's located at apoaps and periaps. And you can see here that the profiles are already different, and they cross also different condensation curve, giving rise to maybe different atmospheric composition. So fitting an energy balance model to our phase curve, we were also able to estimate P naught, which is the average pressure where stellar energy is being deposited, and V wind, which is the average equatorial wind speed, which here is comparable to the speed of sound on the planet. And we also compared our phase curve to general circulation model predictions, where we notice here that these models also seem to underpredict the planet's thermal flux. And so this led us into looking into the radius of EXO-3b. So we use Gaia observations or Gaia data to empirically constrain the mass and the radius of EXO-3b. And to contextualize these quantities, we ran an evolution model of the radius of EXO-3b as a function of age. And so under normal circumstances, after the first gig year or so, a 12th Jupiter mass planet is expected to be much smaller than what it is right now, suggesting that maybe EXO-3b's radius is inflated. Interestingly, if you add an additional 20% of the insolation dumped in the interior of the planet, then the radius of EXO-3b becomes reasonable. And so 20% is a lot. We're not sure. Yeah, 20% is a lot. And so now the question becomes, how do you generate this much internal energy? And so there's many ways of inflating a hot Jupiter, but here we think that there are probably two main sources of energies. So the first is the eccentricity of the orbit guarantees that EXO-3b is experiencing some amount of tidal heating. But in order to generate 20% of the insolation worth of energy, it would have to have been caught in the few million year window when the planet is rapidly circularizing. Another hypothesis here has to do with the large mass of 12 Jupiter mass. And so when you're barely above the deuterium burning limit in mass, it's plausible that it might take you gigayears to finish burning all of the deuterium. And so maybe what we're seeing, maybe this excess flux could be tied to a combination of these two mechanisms. So with EXO-3b, we saw that the age of the planet also matters when we're interpreting our observations. And in fact, eccentric planets have transit features that are relic of their evolutionary history. So I'm hoping that maybe this is something that we can explore with Ariel, ESA's Exoplanet Surveyor, planned to launch in the 2020s, in the late 2020s. So the objective could maybe to design an experiment using eccentric planets to find out what their climate can tell us about their history. In the meantime, maybe we're hoping to acquire more JWST observations of these more moderate eccentric planets in order to test the simulations that we will produce for Ariel. So now looking at hot Jupiters on circular orbits, I'm not the first person today to talk about these GCMs and hotspot shift, but I'll go through it again. So these are general circulation models of a typical hot Jupiter where the background color represents temperature at different locations and the arrows are directions and magnitudes of winds at different locations. And again, one thing that is particular about these models is that all of these simulations predicts strong equatorial super rotating jets, that is causing the planet's hottest region to be located east of the substellar point, represented by the yellow dot. So the first few published Spitzer phase curve had all shown to exhibit some kind of eastward offset or having an offset that is consistent with 0. And for a long time, this was largely interpreted as evidence for the feature that we saw in these GCMs. However, in 2016, we used the Spitzer Space Telescope to stare at Curve 2b with Spitzer, and this is the phase curve that we obtain. So note here that the peak of the phase curve is not exactly coincidental with the secondary eclipse, but rather occurs a couple of hours later. And this corresponds to a westward hotspot offset of 23.4 degrees, therefore contradicting the GCM predictions, but also it stands out from a published phase curve of other hot Jupiters at the time. So while these results defy predictions, the westward offset can be explained by three possible scenarios. The first hypothesis has to do with clouds covering the eastern day side of the hemisphere, hence blocking thermal emission and sculpting our phase curve. However, it's hard to explain how these clouds would have gone there without westward winds, and then the second scenario questions the synchronous rotation of Curve 2b, which could be possible given the young age of the planet. And GCM simulations from Rauscher et al. 2014 have shown that hot Jupiters with subsynchronous rotation can sometimes end up in a regime where you have predominantly westward equatorial winds. And then finally, one way to diverge from the feature that we see in pure hydrodynamical simulations are magnetic effects. So the atmosphere of a hot Jupiter can sometimes be so hot that you have a partially ionized atmosphere. And this means that if there is some underlying magnetic field, the ions in the atmosphere could interact with this magnetic field and disrupt the flow that you would expect from pure hydrodynamical simulations. And so this is also consistent with the inflated radius of the planet, which is usually indicative of an energetic interior. So while all of these scenarios are different, we think that they're plausible because they might be connected to the young age of the system. And we think this is why it stands out. Speaking of other phase curves, so now there are enough of them to allow for a comparative studies. And so we did a preliminary comparative studies where we looked at the night side temperature inferred from these phase curve shown here. And then the night side temperature have revealed there being two classes of giants. So you have the hot Jupiters with constant night side temperature, suggesting tantalizing evidence for night side clouds. And then you have the ultra hot Jupiter, where enough molecular dissociation occurs and that increases heat transport towards the night side. And finally, the last topic that I wanted to talk today are ultra-short period rocky planets. So another benchmark achieved by the Spitzer Space Telescope is the first thermal map of a super Earth, the iconic 55 Cancri. And so many ultra-short period planets have day side temperature that are hot enough to harbor molten magma pool on their day side. Unlike hot Jupiters, these planets are expected to have lost their primordial atmospheric envelope, but instead they could have a thin layer of rock vapor outgas from their molten day side. And so the originally published phase curve shown in black here showed a surprising 21-degree eastward hotspot offset. Another thing that we also notice is that this offset reported seems to be coinciding with a recurrent observation breaks. And so in the past year, I've been supervising an undergraduate student, Samson Mercier, who has been using our SPCA pipeline to try to reproduce these results. And so far, it doesn't seem like we're getting the same fit. So the fit that we get is rather the orange one. And this paper was recently submitted a couple of weeks ago. So if you want to know more about this, you can ask at the end. But the truth is there are still a lot of unknowns about these ultra-short rocky planets or so-called lava worlds. It's uncertain whether they have a substantial global atmosphere with significant background gas and a lot of atmospheric dynamics, or if instead they have a partially collapsing rock vapor dominated atmosphere. And perhaps this is something that we'll find out soon, since lava planet phase curve of 55 Cancri E, GJ367b, and K2141b with JWST are coming soon-ish in the next year. So hopefully these insights are going to help us understand how the atmosphere of these planets has been influenced by their evolutionary history and give us another piece of the puzzle. So I'd like to conclude with two thoughts here. So first, understanding your detector systematics is very important, and we've seen it over and over again through all of these works, but it was particularly a focus of the Dang et al. 2020, where we looked into microlensing light curves. But secondly, the most important thing that I wanted to end up with is that the history of a planet matters. And we've seen some examples here. So first, in Dang et al. 2022 with the internal heating or potential internal heating of EXO 3b, in Dang et al. 2018, where we saw the westward offset of Koro 2b possibly linked to the youth of the planet. And then in the future, we'll find out how this matters for Lava Planet. So I'll leave this summary up, and if there's any questions, I'm happy to answer them.
Do we have any questions for Lisa? Looks like maybe not. Going once, going twice. Okay then. In that case, thank you so much, Lisa, for the presentation, and congrats again on the award. Yeah, so this concludes our TEPS seminar for this cycle. So thank you so much all for attending, and we'll see you. There may be a presentation next month that we'll probably have online, so I'll let you all know more details as that becomes available. But thank you again for coming, and I hope you all have a great rest of July. Take care. Goodbye.
Thank you. Bye.
Bye.